What I'm presenting to you here in this video is I'm giving you the opportunity to have a practice at a few questions based around proof by counterexample. What's going to happen, I'm going to present you with 3 questions and scenarios. I want you to read them, pause the video, go away and have a crack at them, and then come back and check you're working with the working I'm going to present. Now, one thing that's important to remember is that your working may actually end up being different from the working presented here. Now, that is purely because for a lot of scenarios, there are a huge variety of counterexamples that could be picked to disprove a conjecture. Bear that in mind. Some of them follow the same sort of layout and the same sort of format, but bear in mind yours might be slightly different from this, but this video will give you an idea of those. So there's your 3 questions. What I want you to do is pause this video right now, have a crack at them, and then come back and check what you've done, and let's see how we get on from there. So the first question is this one. So for any real numbers a and b, it's conjectured that a squared greater than b squared has the implication that a has to be greater than b. So I want to find a counterexample to disprove this conjecture. Now, a question like this, where it starts to involve squared numbers and you're comparing the position on number lines and the sizes, instantly start to think about involving negative numbers in the calculation. Because if you think about it, if you square a negative, you'll end up with a positive. So you can increase the size of the number while making it a positive sign, but if you then compare it to a positive number, it's actually less than it because it's less than it on the number line. So for a question like this, let's say I said, right, I'm going to let a equal negative 4, and I'm going to let b equal 2. If I then look at a squared, that's going to be 16. If I then look at b squared, that's going to be 4. This here, the a squared b squared part, satisfies that condition that a squared is bigger than b squared. So that satisfies that part of the conjecture. However, if we then look at the second part, which states that because of this, a must be bigger than b, if we look at the 2 numbers that we've got here, actually, a is smaller than b. So this goes against the conjecture that was put forward at the start. So this part here is actually false. So what this does is this is a counterexample. It disproves the conjecture, and we're then able to say that that initial claim, that initial conjecture, is false. Now again, remember, the counterexample you find might be slightly different to this one, but it follows the same sort of logic and the same sort of idea. Bring in negative numbers where you can, and that can help you a great way. Second question that was put forward to you is that for any real numbers a and b, it's conjectured that a over b is less than 1 means that a has to be less than b. Now this comes from if you think about normal fractions. So if you think about 3 over 4. So 3 over 4 is less than 1, 3 is smaller than 4. What that would mean is that holds the conjecture. So yes, logically it would say that that's the case. We've got to find an example that disproves it. And again, I'm going to go back to this idea of working with negative numbers. If I were to state that a is equal to 1 and b is equal to negative 3, what that would mean is that a over b is 1 over negative 3, which is less than 1. So this initial part of the conjecture holds. So that a over b less than 1 part of the conjecture holds. However, if we then look at the numbers for a and b, and look at them compared on a number line, what I actually am able to write in this case is that b is less than a. That goes against that part of my conjecture. So that part is false. So because the whole conjecture isn't true, and I found a counterexample to disprove it, overall, I can say that it's a false claim. The counterexample disproves this, and it's a false claim. Now again, you may have a slightly different counterexample than this, but it follows the same sort of logic as the one presented here. Bringing in negative numbers so that you can look at positions on a number line. This last one, we're going to expand on it ever so slightly. What we're going to say is that for any positive integer n, un, so the term in the sequence, which is given by the rule n cubed minus 6n squared plus 13n, take away 7, gives a sequence of odd numbers, 1, 3, 5, 7, 9, and so on and so forth. So it's asked us to find a counterexample that disproves this. So I need to say to myself, right, this sort of one here is going to be more along the lines of trial and error. I'm going to have to try and find something somewhere that will disprove this. Well, if I were to choose n equal to 1, that would mean that u1 is equal to 1 cubed minus 6 times 1 squared plus 13 times 1 minus 7. So that actually gives us 1, which is the first term at once. So if we were to say, oh, that's the example I'm going to pick, it's the only one I'm going to try, it actually proves the conjecture, then we're leaving it at that point. However, we need to try and think of one that doesn't give us that. Let's say, for example, I'm going to choose n equal to 4. What I'm going to be able to say then is that u4 is equal to 4 cubed, take away 6 times 4 squared, plus 13 times 4, minus 7. Doing these calculations gives me 64, take away 96, plus 52, minus 7, which if I simplify it down, gives me 13 in total. So according to this rule, the fourth term in the sequence is 13. However, knowing the sequence of odd numbers and going back to what we originally had, I actually know the next term in the sequence is 7. So my term u4 should actually be 7 if it's going to follow that pattern. That's what I was expecting, and that's what I've got. So if I pick n equal to 4, there's a counterexample that disproves that conjecture. So I'm able to then say that it is overtly false. That one counterexample disproves the entire conjecture and shows that what it's stating there is actually wrong and not true for every single value of n. These are just some of the examples of proof by counterexample. You have to remember, all you want is one example where it doesn't work, and that kills the entire conjecture dead. If we can do that, we're laughing. And just remember, some counterexamples may differ between scenarios. Just make sure your one holds out, and everything will be fine.